Who are you? What? When? Why? Where? And how are you? What have you made of? Sugar and spice and everything nice. Well, you have a physical makeup, but you're also more than your physical makeup. You have traits. You have a conscience, mind. But we'll look at your physical makeup. But when did you get here? How did you get here? And where are you? And why are you here? First, as I say, we'll look at your physical makeup. You are almost 60% water. Water is a molecule with 3 atoms, 2 hydrogen and 1 oxygen. You have other atoms too, important. For instance, carbon. It can combine with other atoms of other elements and itself to make large molecules, important for you in all complex life. Excuse me. But you are made up of mostly hydrogen. You have more hydrogen atoms than any other atom. Now, have you ever been in a room with other people and maybe you're being ignored, and so you can't be seen or can't be heard? You get kind of mad, you think you might want to explode. Be careful, be calm. Because hydrogen is very, very active. They used to use it in the airships, the Hindenburg, but they blew up. It was the lightest element. It has 1 proton and 1 electron. So now they use the second lightest, helium, which has 2 protons, 2 neutrons, and 2 electrons. But your molecules are made up then of atoms, and the atoms are made up of negatively charged electrons circling a nucleus with protons and neutrons. But the size of a nucleus is to the size of the atom, as a speck of dust is to a football field. So you are virtually nothing at all. You're 99.9999999% space. So maybe that's why you couldn't be seen or heard. You're virtually nothing at all. But if you're nothing at all, and the atoms in the floor are nothing at all, virtually, why don't you just fall right through the floor? Because gravity keeps you grounded, keeps you on the floor. It's a force of attraction between you and the earth. Well, why doesn't it keep on attracting you to the middle of the earth? You never actually even touch the floor or touch anything. You levitate 1 angstrom unit, 10 to the minus 10, meters above the floor. Are you a magician? Well, maybe so. But what force is keeping you from falling through the earth, or walking through the wall, or pushing your finger through your hand? Well, your electrons and the atoms are negatively charged. The same with the floor or the wall. Like charges repel. So that's what's keeping you from falling through the floor, walking through the wall, or pushing your hand through your other hand. You actually never touch anything, or nothing ever touches you. And what's that force called then? The electromagnetic force. Let the force be with you. Now, some days I know you've good days, you have bad days, you have days where everything seems to be, you seem to be elated, other days you seem to be somewhat depressed. You have your ups and downs. Well, physically, you're all up and down. You're made up of up and down quarks. Some say quarks. Your protons and neutrons are made up of up and down quarks. The proton has 2 up and 1 down, and the neutron has 2 down and 1 up. So the proton up quark is a charge of plus 2/3. and a down a charge of minus 1/3. So 2 up and 1 down, a proton, plus 2/3, plus 2/3, minus 1/3, or 1, charge of 1. Neutron, 2 down, 1 up, minus 1/3, minus 1/3, plus 2/3, or 0. Now you've also had days, I'm sure, where nothing seems to okay. The more you try things, the worse things get. You can't seem to hold it together. Everything seems to be falling apart. Well, let's look at your nucleus of your atoms. The atoms usually, except with hydrogen, have a nucleus with as many protons as neutrons and as many electrons as protons. So you've got several atoms with more than one proton. And they're both positive. They're all positive. And like charges, again, repel. So what is holding your atoms together? What's holding your nucleus of your atoms together? What's holding you together? Why aren't you flying up? There must be a force then stronger than the electromagnetic force that does that. What's that force called? The strong force. Let the force be with you. Now, as I say, you have mostly hydrogen. Where did all that hydrogen come from? Well, before the 1920s, no one knew. But then Hubble, looking through the largest telescope on Earth at the time, at Mount Wilson Observatory in Los Angeles, he saw all the stars were going away from the Earth, receding. What's that mean? It means that space itself is expanding. And if it's expanding and going back, it must be coming from a smaller and smaller place. Going back in time, extrapolating how fast it's going, and go back in time, it works out to be 13.8 billion years when everything started. And science does not know how that happened. And they will never know. What does it mean for that there have to be no time? And what was it before time? These are questions that science does not have a definitive answer for. And by definitive answer, I mean they have to have empirical evidence or have to be able to see it happening. And then they should take it back into the lab and test it out and see if their hypothesis is correct. And have another lab with other people corroborate it as well. And it's very difficult to create another universe in the lab. They may have some speculation, but they have no evidence or have not seen it really happen. And the other thing is, Planck, back in the early 20th century, at the time, is discontinuous. What's that mean? Well, you can start off with 1 billion years, go to 1 million years, go to 100 years, 10 years, 1 year, 1 month, 1 week, 1 day, 1 hour, 1 minute, 1 second, 1 microsecond, 1 nanosecond, and keep going back until you get to 10 to the minus 43 seconds. That's 0.00043 times. And you can divide no further. It's discontinuous. He called it a quanta of time. We now call it a Planck time in his honor. So if science says you can't go, time is not anything less than 1 Planck time, how can they say anything then about time equals 0? By their own laws, by their own ignition. And divide something in mathematics by a smaller and smaller number, you get a bigger entity. Divide by 4, you get something 4 times as big, for instance. Keep going back and divide by something smaller and smaller until you try to divide by 0. All hell breaks loose. You get infinity. And what about infinity? It's so unusual. Well, you multiply infinity by 3 and you get infinity. If you add anything to infinity, you still get infinity. So math breaks down, really. We call it a singularity. So at time equals 0, then, you might also say that that's a singularity when they do. And maybe there's something infinite there as well that creates a finite. And science doesn't have the answer for that. And maybe religion does, because we all think, those who are religious anyhow, think there's something infinite, has an infinite mind, that could create the finite. So they say that between the first Planck time and 0 is a multiforce. Of course, religions say there's something that is omnipotent. And at the first Planck time, then, the force of gravity separates from the superforce. And then at 10 to the minus 35 seconds, that's 0.0005, 35 times, the strong force separates from the superforce. And at that time, the space goes through an enormous expansion, inflation. How do they know that? Well, there's some evidence of that, but just an idea. If you inflate, the universe was very uniform then. Just like when you inflate a balloon, the surface becomes very uniform, very flat. There's other evidence as well, but that's one indication, if not a proof. Then at 10 to the minus 12 seconds, you get your electromagnetic force. You also get a fourth force, there are 4 forces, called the weak force. Now, maybe you should be recognized when you're in that room, although you're mostly space. Because you're a radiant person. You radiate when you. Unfortunately, not that much. It would take millions of years times the age of the universe for your protons to radiate away with radioactive decay that is formed by the weak force. Nevertheless, your weak force is important. Without it, you would die. It keeps the center of the Earth molten. The center of the Earth being lead, and if it's molten, every day you have the rotation of the Earth around its axis, that sets up an electromagnetic field, or if you like, a shield, around the Earth. You get a magnetic North Pole, you get a magnetic South Pole. And that protects you from harmful solar radiation and harmful cosmic radiation from outer space. It also protects the atmosphere from being blown away by solar radiation. And you need the atmosphere to breathe oxygen. And also to mitigate anything coming down from outer space and hitting you could cause quite a stir. Meteors, comets, asteroids. It usually burns up most of them in the atmosphere. Some of it lets through, but often they're burned up to be small. And on occasion, over 30 million years or so, it lets through whoppers. They get through hit the rim and cause a lot of damage. Let the force be with you. At that time also produce particles and antiparticles. It's not just science fiction. And then when they come together, they annihilate each other. They form energy. Now, before 1905, all the scientists were saying, well, they're different. Energy and matter is different. There's a law of conservation of energy, law of conservation of matter. Never the twain will meet. Einstein, in his special theory of relativity, said no, they're equal. You guys are wrong. No, he probably didn't say that. Now, I'm not sure if it was Einstein or not, but one of the scientists said, it's not that I'm so much smarter than anybody else, it's just that I can see further because I'm standing on the shoulders of giants. But nevertheless, Einstein did prove that energy and matter are the same. E equal mc squared. Your energy is equal to your mass, that's the amount of material you have, times the speed of light times the speed of light. Now at 10 to the minus 1 second, or 1/10 of a second, your protons. So you get more happening in the first second, really, than the next 13.8 billion years. So you have all those particles and antiparticles come together, annihilating each other. So how did we get, if it's all energy, what happened? Well, 1 second, something happened again that science cannot understand. For every billion antiparticles, you get 1,000,000,001 particle. And you and everything else is made up of particles, no antiparticles, or you would change into energy, blow up. So not only does it not understand what happens at time equals 0, or can't explain it, nor can it happen what happens at time equals 1 second. They try to, as I say, take it back to the lab and come up with an experiment. Every time they tried to change energy into matter, they always got the equal number of particles and antiparticles. Now, for the first 308,000 years, it was so, after the first second, it was so dense and hot that particles couldn't combine. There would be photons, particles of light, protons, electrons, all perhaps in a plaza. But then at that time, cool enough so an electron could be captured by a proton. So what do you got? 1 proton, 1 electron. That's hydrogen. So that's where you got all your hydrogen from. And you thought you were less than 100 years old. Most of your atoms at least, are 13.8 minus 308,000 years old. Now this theory, and you can, usually you have to have the evidence before you can really call it a true theory. It's, but there is some evidence to support it. And it's called the Big Bang Theory. But it was proposed by someone who didn't believe in the Big Bang Theory. According to Hoyle, a good scientist from Britain, he had what is called the steady state theory, or hypothesis. The universe is steady as she goes. It's always been there, always will be, and you may get stars created, but you have an equal number of stars that disappear. He didn't like the other theory, so he derisively called it a Big Bang, and the name stuck. So the Big Bang Theory is named by someone who didn't believe in the Big Bang Theory. Now, as I say, you should have evidence. First of all, how did Hubble know that the stars and hence the light and hence the stars were moving away from the Earth? Well, light can be both, believe it or not, both a wave and a particle, photon. All you have to do is check it to see it's a wave, hold up 2 fingers close together, look through with one eye, and you'll see faint lines in between your 2 fingers. They're called interference lines, where the waves interfere with each other, similar to when you throw 2 rocks in a pool, and the waves will interfere with each other. So, Newton, back in the 16th century, passed light through a prism, and he saw light broke up into the colors of the rainbow, from red to indigo, indigo being dark purple. And the wavelengths of each of those colors are different. So the wavelength of red light is larger, the distance between the two crests, than the wavelength of indigo. Now if the wavelength is bigger, in a meter or so, in one distance, it can't go up and down as many times as if it has the wavelength is less. It'll go up and down several more times. So the frequency then of red light is less than the frequency of indigo light. Now sound is also propagated by waves. You hear a train coming towards you, and the waves are being pushed together, squashed. And the frequency then is higher, and the pitch is higher. And when the train goes by, it pulls apart the waves, stretches them out. So the wave length is larger, and the frequency is less. And the pitch is less. So you hear the train going from a high pitch or high sound to a lower pitch or lower sound. Called the Doppler effect. The same then for light. If light is coming towards you, it's a high frequency, indigo. If light is going away from you, it's shifting towards the low frequency, red light. So looking through a spectroscope, you can see that every color has a different signature, so you can see the stars were shifting towards the red. It's called red shift. Therefore, the stars are receding away from the Earth. And as I say, figuring out how fast it's going, extrapolating back, turns out to be 13.8 billion years. But what about all of these particles? I mean, how did you come up with the idea that in the first second, at the time you go 10 to the minus 12, you get all these particles? You can't really have an experiment until you get to there, because it's so much energy, it would be impossible to get a piece of equipment to well, maybe it would be possible. Well, there is a large Hadron collider, Hadron being anything, particle with mass, that can do this, that. It simulates the amount of energy that you have at 10 minus 12 seconds, and it's a most integrated and biggest machine on Earth. It's a loop 27 or so miles or kilometers underground, with large electromagnetic magnets, with which they have circulate protons in one direction near the speed of light, and then the particle again in the other direction near the speed of light, and have them collide and see what falls apart. Just like a car roller derby, when they smash together, the parts fly off. And so you try to determine what the cars are made of. Well, here you try to determine what the particles are made of. And there were so many particles coming off, they called it a particle zoo. Then they came up with a particle theory, which explains everything that in the whole universe, including you, how everything's made up. There are three pairs of quarks, the up and down, which you are, the charm and strange, and the top and bottom. The last two don't stick around too long. And for each one of those pairs of quarks, there's a lepton. For the up and down, it's an electron. For the other two, it's the tau and the mu. And there are four forces we mentioned before: the force of gravity, the strong force, weak force, and the electromagnetic force. And for each of those forces, there's another a particle called a boson, which gives the interchange of the boson creates that force, the forces. For instance, The boson for the electromagnetic force is light. It's a photon. So when you hold two magnets together and the south poles, they can't get them together, or the north poles can't come together, it's photons of light that are keeping them apart. Boson for the strong force is the gluon. And the boson for the weak force, there's two, the W and the Z, not Z but Z. And the boson for the gravity is a graviton. And then a guy called Higgs said that we need one more boson, a boson that will give mass to the other particles. He predicted that way back in the middle of, the middle of the 20th century, and in 2012 they found it, and they named it the Higgs boson. And all the particles physicists jumped up and down. Because whenever you have a theory or a hypothesis which predicts something, and that comes true, then it gives more credence to that theory. It's closer to the truth. But to try to find the graviton, you need a collider the size of the solar system. So they came up with another piece of equipment called a LIGO, laser interferometer, observance, gravitational observatory, interferometer. Yeah. Uses interference of waves, and they just discovered the gravity waves just a decade or so ago, and or less. Therefore, there must be a graviton as well. And again, that leaves, when you discover that, gives credence to their particle theory. The other piece of evidence for the Big Bang theory, remember I said in the first 380,000 years, photons were in there as well, so would be no light. But at that time, the photon was able to escape, and you're still being hit by light from that era. It's now stretched into a microwave, part of the electromagnetic spectrum. But 3% of your static in your AM radio or in your old TV with an aerial comes from that time. So that's another piece of evidence that supports the Big Bang theory. But what about all the other atoms? Where do they come from? Well, you get all that hydrogen being produced, and then over the next 500 million to 1 billion years, it gets so massive, it gets very hot in the center of the universe, and also the force of gravity becomes so large because of all the mass. It overcomes the electromagnetic force that keeps things from touching, and the hydrogen in the atom touches the hydrogen in another atom, or fuses. And what happens is it fuses together and forms helium with 2 electrons, 2 neutrons, and 2 protons. But it also gives off a lot of energy. Now, the hydrogen bomb is a fusion bomb, and you can see how much energy it gives off when you blow up a hydrogen bomb. So you have all of this energy, and you have gravity trying to attract everything, and you have the fusion trying to blow things up. You have a tug of war between the two, and in the process, a lot of energy given off. So what do you got? Could say Judy Garland. In any case, a star is born. So that's how you get a star. What's the closest star to the Earth? You should know its name. You probably do know its name. You know what it's called? It's called the Sun. So the Sun is a star converting hydrogen to helium and giving off energy in the form of light and warmth. Now a star which is over 4 times as large as our sun, or as massive as our sun, after it uses up all the hydrogen, converts it to helium, then the helium atoms fuse. And then they're used up and form the next element, or another element in the periodic table. And so on. Until you get up to iron, which is a fairly heavy element. I can't remember how many protons and neutrons it has. But the periodic table is arranged from the elements which are the least number of protons and neutrons. In case of hydrogen, just 1 proton, up to more, and from the lightest to the heaviest. But when it gets to iron, it doesn't have enough energy. It doesn't give off energy. It requires energy. So there's no force of fusion there to counteract the the force of gravity. So the star collapses almost instantaneously. And it blows up with such force into a supernova. And a supernova gives off more light than all the other stars in the galaxy combined. Some 100 billion to 200 billion stars. And with all that energy, it can fuse together iron and most of the other elements in the periodic table. But it leaves behind a core with all that, with all the space squashed out of the atoms, called a neutron star. And it's so dense, a teaspoon of that would be as massive as all the stars, all the cars in North America. And now I tried to test that out. But when I took a teaspoon of the neutron star, it went right through my hand, because the force of gravity overcame the electromagnetic force, which keeps everything away, 1 Langstrom unit away from touching me. But it overcame that and fell right through my hand down into the center of the Earth. And of course, when I tried to weigh or find the mass of all the cars in North America, I really gave up after the first 1 or 2. Nevertheless. So you get all that material being spewed into space. Now, a star which is over 100 times as massive as our star, when it blows up, it leaves behind in the core a black hole. Something so massive that even photons of light cannot escape. Escape velocity of a black hole is greater than 10 to the 10 to 7 meters per second. And now figure that to get the very heaviest elements, you need to have either 2 neutron stars or 2 black holes collide to get that energy to create the heaviest elements in the periodic table. But you have all this information, all this, some say information, but all this material that was created in the stars and from the supernovas, spewed into space. What happens to that? Well, gravity again takes over again and forms a 2nd generation star. Our star, the Sun, is probably a 3rd or 4th generation star, and formed some 4.6 billion years ago. Now, 10 years ago, all the scientists were saying, it's a scientific fact, that was the Earth was formed 4.5 billion years ago, and the universe started 4.7 billion years ago. I'm sorry, 13.7 billion years ago. So maybe they found another fact and had to incorporate that into their first true fact to come up with another true fact. But at that time, the lighter elements, hydrogen, would have formed the sun, and everything else, all the other elements and material would have been rotating around the sun. So the lighter ones would, like dust, would have been attracted together with a hydrostatic force, and then as they got bigger, the gravity would bring them together, and they're quite chaotic. So everything was bashing in together, pulverizing each other, and gravity was building up again for bigger and bigger things till you got to your planets and dwarf planets. Figured out there's more dwarf planets than there are planets. And some of those were pulverizing each other. The planets. Figure 1, the size of Mars, hit Earth, hit it at the right angle, 45 degrees. So it didn't pulverize it or didn't bounce off, but it took a big chunk of the Earth out, of the Earth's crust out, which circled around the Earth, and eventually gravity brought it together to form our moon. So our moon is part of the Earth. How do we know that? We'll take a trip around the moon. You see there's only one black spot there. It's a lava lake. But on this side of the moon, there's several. We call it the man of the moon. Well, if you think that's too sexist, look at the moon again, and from the top to the bottom, you see a male and a female kissing. That's why maybe we think it's so erotic. So what's that got to do with the price of moon? Well, the Earth was molten when it started, and the moon was circling around so close. Tidal waves would have been a mile high. And so material was going around the moon as well. So the other side of the moon, facing away from the molten Earth, would have been cooler. And more material would have landed on that side, which is why the moon's crust is some 25 or so kilometers or miles thicker than the crust on this side. And since the crust is thinner, it allows the lava to come up through the cracks and form more of the lava lakes. Asteroids also brought back some rocks which could only have been produced in Earth. So that's why we know the Earth has formed the moon. And it's important for you because figure that complex life like you couldn't survive without the moon stabilizing the Earth. Life itself. Well, what about that one? Because you got all your atoms, but you have to put them together into a working mechanism, right? And when did you get your life? Well, the first 500 million to 1 billion years, it was so hot, chaotic, hot that life could not have survived. But then when life started, it was pretty dull, really. You just have a cell divided into another cell to make 2 cells, and then divided again to make 4. Then you eventually got the cells cooperating with each other, multi-celled organisms. But here's where, if you don't mind, I'll get a little personal. When did you first have sex? The kind of sex that we talk about nowadays, anyhow. Well, some 5 billion years ago. You know that you get half your genes from your biological father, half from your biological mother. And your genes have cells. And the core of the cell, core of the cell is deoxyribonucleic acid, the DNA. And that's where you get all your physical characteristics from. Color your eyes, color your hair, size of your nose, how big you can get, how much you can weigh. And your DNA is like a ladder with rungs in between, two sides of, and it's twisted, so it's called a double helix. And when you grow, that ladder splits in two, and a new left side or new right side comes together and matches it identically billions and millions of times. Except that when it doesn't, there may be something that interferes, maybe a cosmic ray or something, and you don't get a perfect match between the left and right side. And because your DNA gives you all your characteristics, then your physical characteristics could also change. A process called mutation. But you get all the life coming up from the ocean onto the land, and you get your plants and your animals. You're an animal, but the animals require plants eventually. We can eat other animals, but those animals have to, we'll probably, down the chain, will have to eat vegetables, vegetation. Now plants grow, a process called photosynthesis. They get energy from the sun, and oxygen from the atmosphere, and a byproduct they give off carbon dioxide. Plants take in carbon dioxide. Did I say? Yeah, okay. I might get this mixed up. Plants take in carbon dioxide, and through the process of photosynthesis give off oxygen. Animals take in oxygen, and the process I just mentioned before give off carbon dioxide. So it's a symbiotic relationship between the two. Now one mystery, sort of a mystery, is why are there animals at the bottom of the ocean? I just discovered that a few decades ago. Because there's no lake down there, so they can't have plants. So they must have grown then from some chemical process. Maybe the volcanoes at the bottom of the ocean gave off chemicals, and the animals were formed from that. Don't know what else it could have been, but of course it's difficult to come back and prove that in a lab. But there's always one smartass in every group. There's one plant. He thought he'd, trying to grab more of the precious sunlight, so he grew taller. So he had leaves that could gather in more sunlight. And when he died, he didn't rot. And most of the other plants, when they rot, they give back carbon dioxide to the atmosphere, which they had used when they were living. This plant just lay there and was compressed for millions of years into coal. The plant we all call the plant a tree. So back then, of course, there'd be more oxygen in the air, in the atmosphere. So the animals at the time, insects, would have been able to grow much larger because they breathe through tubes. And some of the oxygen is absorbed in the tube. So if there's more oxygen, the tube can be then bigger to let enough oxygen through. So centipedes could be the size of crocodiles, for instance. And then you had the reign of the dinosaurs, 160 million years. They ruled the earth. During that time, the continents were all one called Pangea. Then they split up into more or less the planets they are today. They're still moving, but we don't see it. They're going so slow. Who came up with that idea? Well, you can sort of see yourself that South America and Africa seem to fit together like pieces of a jigsaw puzzle. But before Wagner came along, no one seemed to put two and two together. But he saw that all the continents could be fit together like pieces in a jigsaw puzzle. But that's just a speculation or a hypothesis. You need to have empirical proof, empirical to prove it, evidence. So what he did is he looked at plants, fossils of plants and animals on this side of the Atlantic, and matched them up with fossils of plants and animals on the other side of the Atlantic. And they found that they existed nowhere else on the continents or any other continent. So they must have been together there, and they shared the same space. So that's the second thing he did. The third thing he did is looked at land formations. Found that they started on this side of the Atlantic and continued on the other side. And in particular, he looked at sedimentary rock, and you can lay down the layers in different thicknesses, and found on the other side sedimentary rocks which have the same, exactly the same composure. So they must have been together and split at that point. Fourthly, he looked at fossils in the north and found that they could only have lived in the south. So the land itself must have moved from the south to the north. So was he heralded as one of the greatest geologists or scientists of the time? Far from it, the reverse. He was vilified. He was made the laughingstock of the geological and scientific community. They said that's ridiculous. Their opinion, and the consensus of their opinion, said that we won't even bother looking at the so-called evidence. He died not knowing that he would be vindicated, his theory would be proven to be correct. Rescuing or trying to help out people in Greenland, he was trying to find more evidence. But he stopped and helped out people in Greenland in the snow, walked off, never to know that his theory and he would be vindicated. So here's a lesson that even scientists should follow. Follow the evidence no matter where it leads. And the consensus of opinion, unless it's backed up by evidence, is not worth a cup of coffee. And if it's one piece of evidence that doesn't comply, then you have to turf out your theory or hypothesis, or try to incorporate the evidence and come up with a modified theory. Or in some cases, you can say, well, this theory works fine, but it is only in certain conditions. But 65 million years ago, the age of the dinosaurs stopped. What happened is Jupiter, which has more mass than all the planets in the solar system, and usually attracts a lot of the material from outer space, the comets, the meteorites, meteors, and asteroids, because of its large force of gravity, because of its large mass. And that threw a whopper. It landed and went through the Earth's atmosphere as well. Landed in the Yucatan Peninsula in Mexico. Caused quite a stir. Burned off a lot of the vegetation. And a lot of material was spewed into space from the impact, went around the Earth, and blocked off the sunlight. And dinosaurs, being cold-blooded reptiles, require heat, which is why they become inactive at night and have to come out to eat in the daytime. So the mammals, which were around then too, like you, had to stay underground during the daytime, for fear of being eaten up by the dinosaurs. Can only come out at night to eat find food. They could stay underground because they don't require, they're warm enough, and they don't require the heat to move around. So that was bad news for the dinosaurs, but good for you. Another event, which is good for you, was 10 million years ago. North America and South America came together before they were split into separate continents. That changed the ocean currents, and that changed the climate of Africa. So Africa was used to having trees, could not support the number of trees, and had some grassland. And some of the animals in the trees said, it's getting kind of crowded up here. I'll try my luck on the grassland. And luck would have it, maybe a cosmic ray came down and modified his DNA, and he passed that on to his offspring. And those offspring with characteristics that were better suited to live in the grasslands, and survived and passed on their DNA to their offspring, and the rest is history. So you came about because of a multitude of steps, all of which, if they didn't happen, you wouldn't be here. Your mother and father came together, produced you, and you have half your DNA from your mother, half from your father. So you're physically half of each. And your grandparents, you're 1/4 of each. And then going back and back and back in time, for over 1 million years, it would be what, 160,000, or you'd have to work it out. That you're part of. And then you're on a planet just the right distance from the sun. The Goldilocks position. Not too hot, not too cold. If it was any farther away, the water would be frozen, and any closer, the water would be evaporated. And since you're 65 or 60% water, you need water. Life needs water, we think, to live. Now, looking for life way back in the universe itself, Carl Sagan, a great scientist, was one of the first to look for intelligence in the outer space and search for extraterrestrial intelligence, SETI, trying to find signals from outer space that could only have been produced by someone intelligent, some intelligence. He also said that he produced a documentary called Cosmos, which explains a lot of things. And he said that you are stardust. Well, not to quibble, but all but your hydrogen is stardust. And he also called the Earth a pale blue dot, because when you look at the Earth from outer space, everything is dark except this one little pale blue dot, and everything that ever happened in all of history, as far as we're concerned, happened on that one pale blue dot. And if one part, he likened it to the organism. So if one part of the organism isn't well, it affects every part of the organism. Therefore, we should make sure that we don't harm any part of the earth, wars and so on. Neil deGrasse Tyson, who was influenced by Carl Sagan, has gone on and created and monitored several Cosmos series. But now, in the last 10 years or so, we're thinking that could be life in the solar system. Because the moons of the planets and the dwarf planets are worth looking at. They seem to have water or ice, and underneath the ice there could be water. And I forget the planet of Jupiter, is it Io? When it has volcanoes, it spews out water, not lava. And the moons of, they're covered with ice, but underneath there would be water, and there could be microbes, living things. The water is kept, even way out by Pluto, is kept from freezing, from the tidal waves, from the force of tidal, from their planets, the main planets. So, but as far as we know, the only ones that we know for sure is the Earth that has life. Looking at Mars, and they now have us. They have satellites that try to look for planets around the stars, and we see now that there seems to be planets around almost every star that we look at, maybe more than one. So we try to find a planet that's in the Goldilocks position and see if there's any signs of life there. Maybe there'd be oxygen in the atmosphere or water vapor. There'd be signs of life. And on Mars, there's water there too. And Mars may have been more conducive to life, may have had a better atmosphere back there, because unlike Earth, its core would probably be not molten, because it's not as massive, and so it wouldn't have the atmosphere that helps us on Earth. So they set up a satellite now. Well, Perseverance. It's digging up piles of dirt to look for, so they can send another probe up and bring it back and look for living or non-living microbes. But as I say, the only life we know so far is on Earth. And then, of course, Earth is one of, as I say, several planets in the solar system. The solar system is one of several stars and solar systems within over 100 million or a billion or 200 billion stars in this galaxy. And this galaxy is one of over 200 billion galaxies. And all those stars are responsible for all your elements, all your atoms, other than hydrogen. What happened over the last, 9 billion years. So you could have one carbon atom, for instance, that's 12 billion years old in one finger, and another carbon atom that's 7 billion years old in another finger. Coming from different solar systems, different galaxies. Over the 9 billion years or so, from the Big Bang to when Earth put it all together, the solar system. And then, of course, you got your hydrogen. That 1 in a billion chances of that, 1 in a billion chances of that to get your particles. Otherwise, you'd be all energy. And you got 4 forces in the first second. Force of weak force keeping you safe from solar and cosmic radiation and keeping the atmosphere there to let you breathe and to mitigate anything hitting you from outer space. You have the strong force stopping you from flying apart, and the force of gravity keeping you grounded on the Earth. And of course you have this universe with this particular the particular constants that are that if they were any different, you wouldn't be here. For instance, they really don't know why all the forces and constants are exactly, some of them exactly the way they are, because if they were slightly different, you wouldn't be here, the universe wouldn't be here. One example would be the force of gravity. If it was any lighter and any less, wasn't as strong, then they wouldn't have been able to bring together the hydrogen and eventually form the stars and you. And so the universe would simply be all hydrogen. And then if it were any stronger, once it produced the hydrogen, it would then attract it back into a big crunch. Wouldn't be able to form the stars. The one that's really an enigma, or the mystery, is the cosmological constant. Einstein put it into his general theory of relativity. I think it was called lambda. And that would allow the universe to expand or contract. He took it out like everybody else thought, well, the universe doesn't expand or contract, so it just is. And he called it the biggest mistake in his life. But the biggest mistake was thinking it was a mistake, because it's now needed to explain how the universe expands. So they said, well, let's look at that. Let's figure out how much it expands. So they looked at it, and then let's measure and find out exactly, practically, how much it is expanding. Because surely it's going to slow down. It'll get colder and then go back and maybe into a big crunch. To their surprise, they found it's not even slowing down, it's accelerating faster. And they're at a bit of a loss to understand why. They come up with a hypothesis why that could be, but they really don't have evidence, so they can't really call it a true theory. They say that space is not empty, it's full of virtual particles and antiparticles. And just as with particles, when virtual particles come together, they annihilate each other and form energy. And the energy they form is dark energy because they don't know what it is. And as the space expands, get more space, well, you get more virtual particles and antiparticles, and you get more dark energy. Whereas gravity, which keeps everything pulsing together, uses mass, and the mass doesn't change. And so dark energy is winning over gravity, and the universe, as a result, is accelerating. They also figure that dark energy consists of 70% of the universe. They're in the dark about that. But they also figure that there needs to be more gravity or more mass. 4 or 5 times as much as they can see. Now, why do they say that? Because of when a skater spins, they move their arms out, they slow down, they move their arms in, they speed up. And of course, Pluto goes around the sun much slower than Mercury. But when they looked at how the stars go around the center of the universe, the center of the galaxy, Milky Way galaxy, does not compute. They need more gravity, 4 or 5 times as much. They need more mass. Don't know what it is, so they call it dark matter. And it's not composed of anything that matter is. It doesn't have protons or quarks or molecules. They speculate, think it may be WIMPs, weakly interactive party. Excuse me. Yes, wimps, or some even say macho standing for someone else. And they're actually trying to see if they do exist in the International Space Station and at CERN. But as far as I know, they haven't discovered any so far. And that consists of 20% then of the universe. So the scientists really are in the dark for 95% of the universe. And the other 5%, they don't know much about, they don't know the fundamental question about that either. Because they have two different theories which are incompatible. So at the fundamental level, science cannot give you the answer of how you got here and how things work in the fundamental level. So we've sort of looked at where you came up and how you got here, when you started. But what, in terms of what you're on, we've looked at your DNA and we looked at all your, where you got your atoms from. But there's some other trees too. For instance, your DNA gives you a good idea of how much you're going to weigh and how tall you are. Those are physical characteristics. I mean, there are some nutritional value, nutritional things that happen as well. But there are limits at least put on, physical limits put on by your DNA. And before the 1600s, people really didn't understand weight. What is weight? So Newton, back in the 1600s, he saw that the apple fell to the, and the orchard fell to the ground. This is outside of his house, and he said, "Well, there's an attraction between the apple and the earth." And he came even up with a formula. He said it's proportional to the mass of the apple times the mass of the earth divided by the distance between the apple, center of the apple, and the center of the earth, squared. We could say it's equal if you like. You just have to add a constant to make it equal. And that applies for any two objects. Now, again, although maybe you don't realize that you're in your room, that you're virtually all space, nothing at all, and you radiate, but not that much, you are nevertheless attractive. You are attractive. You are attracted to other people, and other people are attracted to you. So you say, no, I may look attractive if I'm far away, but when I get closer, you'll see I've got flaws, mainly maybe I'm overweight. I weigh too much. But no, the closer you are, and the bigger you are, fatter you are, the more attractive you are. Your attraction is equal to your mass times the mass of the other person, divided by the distance between the two of you, squared. Now you may not notice all that attraction because you're not massive enough, or the other person isn't massive enough. But go outside. You'd be more attracted to a mountain, and the mountain would be more attracted to you, or you'd be very well attracted to the earth. So slide an instrument between you and the earth, and you can see how attracted you are. It's called a scale. And that's your weight. So your weight is equal to your mass times the mass of the earth divided by the square of the distance between you and the center of the earth. Center of gravity of the earth, or say center of the earth. So you want to lose weight, climb a mountain. the distance is greater, therefore you should weigh less. Or go on down into the mind. This is shorter, so you should weigh more. Or go to the equator, because the equator is a bit farther away from the center of the Earth. The Earth bulges at the equator, so you should weigh less. Or at the North Pole, South Pole, you should weigh more. But looking at the surface of the Earth to the volume or size of the Earth, it's the same like as compared to a billiard ball. So it's very smooth. Not enough to notice. It's there, but it's too small to notice. But go to the moon. The moon is only 1.2% as massive as the Earth. So you would only weigh, if you're 100 pounds, you'd only weigh, I think it's 62, sorry. You'd only weigh 16 pounds. That's all. If you want to get some Olympic records, if you could jump 10 feet on the Earth, you could jump 60 feet on the moon. Now, I think I kept leaving you in bed. You're not really attracted. The other person isn't attracted to you. They fall for you. You change the space around you, form a well around you, and they fall into that well. Something like when you stand on a trampoline, you form a well or an indentation, put a basketball on the trampoline, and it falls for you. It falls for you, and the closer it gets, the faster it falls. So Einstein said in his general theory of relativity, gravity is not the force of attraction between two objects. It's a warp in space-time. What's he mean by that? Time and space are changing? It's ridiculous. And a lot of scientists said, it doesn't sound cricket to me. And maybe they should be. You should be skeptical unless there's evidence, empirical evidence. And this he came up with a thought experiment. So there wasn't really any physical evidence. And so some of the journalists said, "Oh, listen, there's a consensus of opinion that you're wrong." And what did Einstein say? All I need is one scientist and one piece of evidence to prove it's wrong. I don't need the opinions of all the other scientists. And they got that evidence. They took it back and tried it out in a lab. And the lab was the solar system. I'll explain why later. Now Newton, besides saying that there's a force of attraction between two objects, he says momentum, law of momentum, everything will keep going unless there's something there to stop it. Aristotle before said, no, everything comes to a halt, grinds down to zero. And how does it keep moving? Well, you need the hand of God to keep it moving. Newton said, no, you need gravity and the fact that, and my two laws to keep things going. Take a cannonball and a cannon up to the top of a mountain, drop the cannonball down, and it falls down just like the apple does to the ground and below. Shoot it out of the cannon, and it can go a kilometer, a mile, before it drops to the ground. Shoot it harder, and give it more momentum, and it will go halfway around the Earth before it falls. Harder again, faster again, goes all the way around the Earth. Harder again, it goes all the way around the Earth. It keeps going around the Earth. So the law of momentum and law of gravity keeps the moon going around the Earth. don't shoot it faster than 25,000 miles per hour, he reached the escape velocity of Earth and keep going out into space. Einstein said no. What keeps the moon going around the Earth is a warp in space-time. So consider this experiment then, another thought experiment. Take a rubber sheet representing space-time, or just space in this case. Talk about time later. And get two ball bearings, one large one and one small one, and place the larger one on the larger one representing the Earth on the rubber sheet representing space. And take your smaller ball bearing representing the moon, roll it across the rubber sheet representing the space. And depending on how massive each of the ball bearings are and how close it comes to one to the other, and how fast it is going, it'll either go right by, or it'll hit the indentation caused by the ball bearing and be deflected, or the moon will hit the warp caused by the Earth and be deflected, or it'll hit that indentation or and go around the other ball bearing, or the moon will go around the Earth, because the Earth has created a warp in space around itself because of its mass, and the moon has fallen into that. It keeps on going around. So when they tested that hypothesis or theory, they waited for a solar eclipse. And they looked at the stars behind the sun, and they found that they had been displaced. They appeared in a different position. Because when the photons of light went around the sun, they went into the warp caused by the mass of the sun and were deflected. So they appeared in a different place behind the sun. And that's when Einstein became very famous. Now the other thing another trait, your physical trait, would be your height. And there may be an advantage to be higher, taller. Eisner, who's over 2 meters tall, 2 meters or more high, it's got the fastest consistent serve in tennis. He has a better leverage. Roddick also is one of the fastest serves, and he's a mere 6'5" inches tall. Yeah. But if he wants to appear, quote, more normal, quote, then you have to measure yourself in larger units. Measure yourself, say, in a kilometers. So you'd only be 2 1,000ths of a kilometer. Or measure yourself in the distance, say, from the surface of the Earth to the center, 4,000 miles, I think. Or the distance to the moon, some thousands of miles away. Or to the sun, some millions of miles away, I think. Or at least to stars, which are millions away, miles away, or billions of miles. The farthest away star that we know of is 13 billion. Is the yeah. But when you get up to those large units of measurement, you need to have a better unit of measurement, and then what they use is the speed of light, the distance that light will travel in that particular distance. So, for instance, the time it takes light to travel from the moon to you is 1.2 seconds. That's why Armstrong, there was a delay when Houston sent him a radio signal, part of the electromagnetic spectrum, and he had to reply. So it was 1.2 seconds for it to get there, another 1.2 seconds for the answer. Lots of split seconds for him to decide what to say. So it was about a 3-second delay. And so we say it's 1.2 light seconds away. And the light from the sun takes 8 or 9 minutes, so that's 9 or 8 light minutes away. And to a star, it could be millions of light years away. The farthest away star that we know is through the Hubble telescope is 13 billion light years away. So when you're in that room talking to someone, you want to know how they are. How they are at that time when you see them. But you never see them as they are now. You only see them as they were billions and trillions of Planck times ago. The time it takes for light to reach you from them. So you can never, ever know how things are now. Now, if you want to appear a little taller, say you're 1 meter, you want to appear more, quote, normal, measure yourself in smaller units. So measure yourself in centimeters. So if you're 1 meter tall, you could say, well, I'm 100 centimeters tall. Or I'm 1,000 millimeters. Or I'm 1.6 times 10 to the minus 35 Planck lengths tall. Planck length, well, a Planck time is the time it takes light to travel 1 Planck length. So where are you then? You are somewhere located between 1.6 times 10 to the minus 35 meters and 13 billion light years. You occupy only a small position in space. So Einstein really, it's a world vision, how things work with his mass. Was he given a Nobel Prize for that? By the way, you can derive Newton's laws from Einstein, but we normally just use Newton's laws because they're practical, easier to use, good enough to land men on the moon, and good enough to shoot satellites farther than they can go under their own steam, because they use the gravity of other planets. Now, I also did mention that if Einstein said that it's warp of space-time. So we talked about space, but time itself then varies when it reaches a large mass, approaches a mass. It slows down. Now again, we don't notice that because basically we're all the same distance away from the center of the Earth, and we're all located in the same ring of the warp that the mass of the Earth gives us. So there again, we maybe don't need to use Einstein's theory, except if you want to find out how Mercury rotates around the sun, because Mercury is very close to the sun, or closer to the sun, and it's more affected by the warp caused by the mass of the sun. You need Einstein's equations to more definitively describe the rotation of Mercury around the sun. And also, if you're going on a trip, if you want to get lost, you better use Einstein's general theory of relativity. Because time on the satellite runs faster than time on the Earth. What's this? Time, and not only space, but time changes as well. You'd have to have a atomic clock to measure it. But if you don't incorporate that in your GPS will be out in 2 hours. You'll be lost. And time as well has another characteristic that we don't normally run into. The faster you go, the slower time goes. This seems like craziness, because we don't recognize that because we don't go fast enough. I mean, if you could measure it, you would, but it's very minute until you get up near the speed of light. Consider this experiment, thought experiment as well, if you don't think that that's possible. Very simple. Have your friend go on a train, and when the train goes 100 miles an hour, have him go up the front and throw the baseball 100 miles an hour. So the baseball will go 200 miles relative to you. Forget about diffraction. Then say, well, wait till the train goes 3/4 the speed of light, and then go throw the ball at 3/4 the speed of light. How fast will the ball go then relative to you? It can't go 1.6, 1.5 times, because it's constant. It is 1. Something's got to give. The distance you go is how fast you go and how long you go. How fast you go can't go faster than the speed of light. That's what time has to, V equal to Vt. Time has to slow down to compensate. So, you want to time travel? Well, yeah, I showed you maybe before. You can time travel. All you have to do is look out into the sky, and you see something that's happened in the past. There could be stars that have died 1 million years ago, and yet the light is still coming towards you. You're just seeing the ghost. So you're looking at ghosts. The star's already dead, but light doesn't know it because it keeps on coming down. So in that sense, you're looking into the past. If we want to look into the future, then get on a rocket and travel close to the speed of light for a period of time. Depending on how close you come to the speed of light and how long you travel, when you come back, you have aged less than the people that you left behind. Time slows by, slows down the faster you go. So your friend and you left on the ground could be hours, years, millions of years, billions of years older when you come back. Don't come back when he's 5 billion years older, because he may not be on Earth. The sun could have swallowed up the Earth. So in that sense, you can travel in the past and in the future. So as I say, the Einstein then gives the how things work, how the world works when there's mass, a massive level. But there's another world vision as well at the microscopic level. It's the quantum world. And Einstein, did he get a Nobel Prize for his theories? After all, it does show how everything works. And there's been no evidence ever to dispute it. No, but he got a Nobel Prize for his contribution to quantum mechanics, or quantum field theory. Photoelectric effect. He showed that when a photon of light hits an atom, it releases an electron. And you use that, for instance, when the door starts to close on an elevator, it doesn't come and hit you. It opens again because there's a circuit break from the photoelectric effect. Or the car, the garage door doesn't come down and hit the car when you drive it through. So you can thank Einstein for that. He didn't like this other world vision because it relies on probabilities. His is deterministic, no probabilities involved. He said, God does not play dice. He spent most of his career trying to incorporate the quantum world into his one. And many other scientists, theoretical scientists, are doing the same. But the quantum world, if you think Einstein's world is weird, changing time and space, the quantum world is even weirder. Heisenberg, another founder, Planck was one of the founders, said time and space is discontinuous. And also Heisenberg said that if you have two things that are related, the more you know about one, the less you'll know about the other. For instance, if you have want to know how fast a particle is going and where it is, position, the more you know about its speed, the less you'll know about its position, and vice versa. Not because there's some problem with measurement. No, it's reality at the quantum world. We don't experience that at the real world. Another founder, Feynman, he said, anyone that says they understand quantum mechanics doesn't understand quantum mechanics. He helped out on figuring out an easier way to figure out the mathematics required in quantum mechanics. The classic experiment to show how weird quantum mechanics is, quantum field theory, is a double slit experiment. You pass light through two slits and see what happens on the other side on the wall. Now you think maybe you get two lines, one on the left and one on the right. No. You get several lines. And that's because light can be a wave as well as a particle. And I said before, when you look through your two fingers, you see that waves interfere with each other. So, but then when you observe the light before it goes through, just look at it. And you only get the two lines. So somehow it's changed from a wave back into a particle, just by observing it. So pass one photon at a time release one photon at a time. It has to either go through the left or through the right. And therefore, you should either get a line on the left or a line on the right. You get interference lines. The photon has interfered with itself, or it's gone through the both slits at the same time. And observe the one photon at a time when it goes through. And over time, they get to only the two lines, left and right. So as Feynman says, anyone who understands quantum mechanics doesn't really understand it. And now they're saying in quantum field theory that everything, electrons, everything, start off with waves before they convert it to particles. So again, maybe religion can come in and help as well, because is there someone up there looking at everything that's going on in the universe? Looking over you? Someone even that you can communicate with? Well, as science really can't refute that. As a matter of fact, he thinks that You know, you need to observe things for things to work.
Mm.
The other thing, as I said before, is that all the parameters, this was the word I was trying to find, that occur that explain how you got here. Have to be, some of them have to be exactly as they are. If you change them slightly, you'd be out. But the other thing is that how do you get all these equations and theories and hypotheses, and how do you eke them out of the universe? Before 1905, you had the law of conservation of energy, law of conservation of matter. You had all of Newton's law of gravity, force of gravity, and momentum. The laws, Charles' law, Bohr's law. And after in 1905, you had Einstein's two theories of general relativity and special relativity, and all the equations and theories from a quantum field theory. What is it? Maybe it's the other way around. Rather than getting all those theories from the universe or from reality, it's the theories that are creating the universe. We create virtual reality ourselves. We have performers that have performed in the past and since died, and we put them up on stage as a hologram. So they were seeing them perform a concert that they performed before they died. It's virtual reality. Don't know whether they clap or not because they're already dead, right? After the performance. But you guess you need something a little more powerful, omnipotent, omnipotent, a little smarter, omniscient. And something that happens everywhere, omnipresent. Something that's looking down everywhere to make you into a particle, make you consistent particle. And so you could, and here's where you could say then, science does not have all the fundamental questions on how you got here. And we're just talking now about your physical makeup, but of course you have more than your physical makeup. You have traits, conscious, so on. Now, Persinger at the university in Norwegian University in Sudbury, he did an experiment with students. He put helmets on their head. First they were hockey helmets, and put magnets on the helmets to measure the measure the brain waves. Then he put the students. This was unbeknownst to to the students what it's all about. He put students in the isolation booth. Not sure. I guess he put them in one at a time, and observed what happened to the brain waves. He saw that the left brain had closed down, and the right brain became much more active. And he brought them out and asked them what they experienced, and they said they experienced out-of-body experiences. They would look down on the body, they'd be above it. Saw tunnels of white light. 4 to 5, they said these things. They felt someone was beside them or behind them. Some said they saw demonic creatures. Some said they saw God. As a result, it's been nicknamed the God helmet. So is there another sphere than over and above the physical? Now, scientists debate that. There's some scientists that say, no, this is all can be explained by how the brain works. Others who once said that now have changed their mind because they've gone through that experience. And they say, no, it could not have been the way that scientists describe it. There's something different. In particular, life after death. Everyone, documented cases of what happens with near-death experiences. The same sort of phenomena. Out of body experiences, tunnels of white light, demonic region. There was a Australian training for the Olympics cyclist. He was hit by a large vehicle, knocked out the left side of his body, had to undergo a multitude of operations, I think up to 10, and many times he had out-of-body experiences, and he said he didn't want to come back because it was so great, no pain or anything. He was had exaltations. Somewhat like the you get with evangelistic religions. Now, religion, of course, we do. People who are religious think that there is a spiritual world, something over above the physical world, and even someone above, someone infinite, above the spiritual world, that created everything and is still there looking after you. Now, there are several different religions, and so how can you say are they all right, or are they all wrong? Well, it depends how dogmatic and how fundamental you are. If you think that your religion is the only religion, everybody else is wrong, then how can you square that with everybody else that thinks theirs is right? But if you then think in the fundamental basis, that all of you have the fundamental, all religions have the fundamental philosophy or tenet, that there is something over and above the physical, something spiritual. The most fundamental religion would be the Islamic State, and someone from the CBC, Canadian Broadcasting Corporation, Sullivan, went over to interview a prisoner from the Islamic State in Iraq. And what he said is, if you don't practice our religion exactly as we say, well, if you recognize Abraham, we'll let you go. Otherwise, you will be basically terminated. And their religion states that you have to think, say, and do exactly what we say, what it says, even to the extent of wearing the same sort of clothes. And if you don't, you have to convert, or else you'll be killed. Or women under 40 will be sold into slavery. And this is what he said. But nowadays, I think most religions, especially Christian religions, are more are all tolerant. That's the word I'm thinking of. More tolerant of other religions. They don't demonize them. Yes, there are different ways. In the Christian religion, we think Christ is the embodiment of God. And the Muslim, they think Muhammad is a disciple and communicates with God. And Buddha thinks there is a spiritual world of which they can contact through transcendental meditation. So, I guess depending on how fundamental and how dogmatic, you can say that all religions are not. Do not conflict. They're all the same. And we can see where science is in no position, really, to say that there is not this spiritual world. What happens at time equals zero? What happens when you have these near-death experiences? And what happens at all the other things that happened that happened for you to exist? So you can say, and we do, I should have mentioned as well that even in past and religions that we now would probably call superstition or pagan, they still believe that there's some spiritual world. Columbus sailed the ocean blue in 1400 and was it 82, 92? Came to the Indians and the Americas and asked for food, and they said no. And his crew was starving. So he told them that their gods or their spirits, they believed that even inanimate objects have spirits, would be angry. And to show their anger, they would swallow up the moon in 4 days. And when there was a lunar eclipse, he got his food. Now, I'm not sure if that is, I haven't checked that out, but I've heard that. I'll let you check it out and see if it's true. And even people that don't have a particular belong to a particular religion, that they still believe in the spirituality, that there's something out above the physical world. And also when you say you can't understand something, people say you can't understand something, I never will. You often say, well, God only knows why that happens, or God only knows why that doesn't happen. And when something happens that's fortuitous, you say, thank God that happened. Or when it's deleterious, you say, thank God that didn't happen. And for instance, you could say, thank God there's a force of gravity that keeps us grounded. And thank God the electromagnetic force is greater than the great force of gravity. Otherwise, we'd fall right down into the center of the Earth, into, say, a black hole or singularity. And God only knows where that is. I thank God the strong force is stronger than the electromagnetic force, otherwise we just fly apart. Thank God the weak force, have a weak force which keeps us safe from harmful cosmic radiation, solar radiation, and materials falling from outer space on us. So thank God there's this universe that has all the right parameters that allows me to exist. Thank God every one of these steps that we outlined before happened, otherwise I wouldn't be. So whether you want to do that literally, or whether you can say it's just for random accidents, fortuitous as they may be, that you got here, it's nevertheless miraculous that you got here. Who are you? You are a miracle in the story.